Hello students. Today's class we'll start off with the last topic in the third module, that is worm gear. Unlike the previous three gears which we saw, this one has a little bit different procedure. You can see in the figure on the right, you have an actual screw. This is also called a worm. Okay, a worm and a worm wheel. So that's what it's designated as. So this is called as is essentially a screw. Okay, just like the lead screw of the lathe machine or something like that. So it is similar to that. It is just a threaded screw kind of a thing, which is also called as a worm. And this is meshing with maybe the worm wheel. It's called as a worm wheel, which is synonymous to the spur or a helical gear. Okay, you can see the grooves. They are a little bit or having a radius. They're not exactly similar to the spur or helical gear, but somewhat synonymous to the spur or helical gear. That's how it is categorized. So this meshes with either a spur or a helical gear, and this screw can also be used as a nut, stationary in place. This can be mounted onto a carriage or even a piping mechanism kind of a thing, like opening, valve opening and closing mechanism. So those kind of applications, these worm gears are used. So I'll go briefly into uh, what is this worm gear is and where it is used. A very brief introduction, and I'll tell you the procedure on how to solve numericals in today's class. Okay. So worm gears are unique in a sense because these cannot be back driven. Okay, you can see in this figure we have a cam sort of a mechanism, cam and follower sort of a mechanism where it is only moving in one direction. Okay, you can check it out in this GIF here. Okay, it's just you can just operate it in one direction. You can see the whole worm is moving in one direction only. Okay, so this worm wheel, it is rotating in only anti-clockwise direction. So in this retracts, you have only the linear motion of this worm. Okay, so that's where it comes in handy in most applications in while using in crane and those sort of applications. Right? So if you see axis wise, what all keywords you have to notice is this axes are not parallel. So the axis for this worm wheel and the axis of the screw, they are perpendicular, right? So they are perpendicular to each other. So therefore, they are not intersecting and they are not parallel. So that's how it is. Non-intersecting, non-parallel type of worm gear. Then how else are they categorized is they are characterized by very high reduction ratios. Okay, the speed reduction ratio is very high. It may go up to 1:100 speed reduction ratio. So whenever you need a drastic reduction in the velocity ratio, and that time you use worm gears. Right. So because of this very high reduction in the ratios, you have excessive heat being generated. So there's a lot of heat generated in this worm here. So thereby, this worm is usually made up of phosphorus bronze, right? So worm is always made up of phosphorus bronze material, and this is synonymous to a spur gear or anything. So this can be made of anything, but only the worm for better heat dissipation it is made up of phosphorus bronze. This is one such use of the worm and wormy. This is actually a crane photo taken from a crane. You know, when hoisting, when lifting applications, so it moves only in but whatever direction the worm moves. That's one such application. So the advantage here is a very high speed reduction. Okay, as high as 100:1 can be okay, and it is smooth. The operation is very smooth and it is very silent. overall. Okay, so and also they are compact. So unlike the previous two gears where you had a very big area, very huge area, here you have a smaller volume to cover. So they are very compact, and self-locking can be achieved. Okay, just like in this worm and worm wheel, self-locking can be achieved so that the gear moves in only one direction. So when you see the disadvantages, they're relatively low efficient. The efficiency is very low because drastic reduction, and there are a lot of losses with respect to heat, generation of heat and stuff. And because you're using phosphorus bronze for the um, material here, that is worm, so there is a considerable increase in cost. And also because there is a heat generation, you have to enclose this or leave it open to the atmosphere like this and apply some grease or something to dissipate the heat, or you have to enclose them in a casing which is filled with oil, or you need to dissipate the temperature. That's you need to use a coolant of some sort. And power transmission is low in this case of worm gas. So only up to you can transmit 100 kilowatts of power at a maximum. Right? So if you see the starts, so there is something called the number of starts. You may also have come across this when you're going through the threads. Okay, threads also have single start in power screws. Maybe in the first DME1, you might have come across number of starts in a thread while designing the power screws. So start means how much it moves, how much distance, linear direction, how much distance in the linear direction uh, it moves. That is the whole worm. It moves along the linear direction in one revolution of the worm. So that's what it means. So you may get double start, triple start, and multiple starts in case of worm gear. So what happens in double start is it moves double the linear distance. It moves here than in the single start. So in double start you have twice the linear moment. Similarly, you have 3 times the linear moment in a triple start kind of arrangement. So that's the advantage. That's where the linear motion comes into place. So this will be used in the designing part when we are using, and this should be noted whenever we start the numerical, right? Whether it's a single start, double start, those kind of stuff. So if single threaded, it gives a large speed reduction and the efficiency is low. So lesser the number of starts, you can say lesser is the efficiency and more is the heat generation, because it moves very slow. When motion is transmitted from the worm wheel to this worm, what happens is the heat generation is more and the linear motion is not that much. So that's why we use multiple starts to increase the efficiency. We want to increase the efficiency and reduce the speed reduction. So in those times, you have to use higher and higher starts. So let us see some applications. So as to where this worm gears are used. These worm gears are used. Right? So in manual applications, if you see intermittent mechanisms, for example, in hand wheels or gate valves, so those kind of stuff, so they're used. So it's usually essentially half of the helical gear is used here. Half of a spur worm gear is used, and you have a hand wheel, and you have worm, which is this is used for lifting or even in gate valve applications. So you can see in the housing when you start rotating this using manually, this whole housing it lifts up. So that's how it is used. This is used in manual applications like closing of gate valves and hoisting kind of a stuff. And this is one other manually operated kind of a mechanism where you can turn this worm wheel inside this mechanism. This is similar to the previous one. Okay, similar to this worm, and you have a worm segment, and this is a gate valve which opens gradually. So slowly it opens up, and you can control the flow of fluid into the whatever you're trying to control. This is I think motorized kind of a thing. It's the same mechanism. You can see this is for a lathe machines. You might have come across this in the carriage. The lathe carriage which moves, no? So this is rigidly fixed on both ends. So when you start rotating this here, so what happens is the whole lead screw. So this is the lead screw of the lathe machine. The lead screw which is housed in the worm. When you start rotating this, so this whole carriage it starts moving in the linear direction. So the lathe machine is one such application. So this can be used both ways. So this can be used like in motorized, or you can do it manually, switched off and on kind of thing. And also this can be used in continuous operation, like automatic feed whenever you're giving in a machine. So that time it can be used. This is one more application of this worm gear. So this is a motorized speed increasing. For example, this is a supercharger of car. This can be used in supercharger applications. Right. So you can see there are two worms. There are two worms where air is taken in from one side, being compressed, and then it goes on to the discharge where it enters the engine, the diesel engine, preferably. So this is another application. So when this moves into the screw, there is no worm wheel here, but we have only the worm. So one such application in motorized application. So here also it is made up of a softer material relatively, like a phosphor bronze, so to dissipate the heat and stuff. So, right, these are all the applications of where we can possibly use, or already we have used, the worm gas and worm wheels. We can use it in on a crane, or in case of lifting mechanisms, automatic lifts, manual lifts, screw jacks. Then these are pipe valves, lathe carriage, used for automatic feed and stuff. Then a supercharger. So all these are typical applications of worm gas. So next, moving on to the terminology. So this is taken out from extract from your data handbook. Okay, it's 12.13a. We'll use the same terminology throughout, and also we'll find the dimensions for this. Right. So first, starting with the worm, you have the hole depth, which is including the addendum, dedendum. It's synonymous to screw thread, but we'll try to split it in between. The worm pitch diameter, the pitch diameter, that is D1, and you have the axial pitch, which is distance between two feet, and you have the lead. The lead is the linear distance. It moves in one revolution of this worm. So one revolution here, the lead moves at a certain distance, and you have the angle, helix angle, uh, shown as gamma. So the notation we use here will be gamma, and you can see the worm wheel also here. This is a cross section of the worm wheel. Okay, so this is a little bit radius. This is unlike the previous two gears. Okay, only in shape, only in the top shape it may differ a little bit, so that to reduce friction and stuff, it is given a curvature. Okay, because as you know, there are heat generation is inherent in this type of gears. And again, here you have the pitch diameter, D2, throat diameter, and outside diameter. So pitch diameter being the main dimension, and all depending on that. So pitch diameter D2 and D1. So again, here this worm is considered as a pinion, synonymous to a pinion, and worm wheel to a gear. Right? So pinion gear. So that's how it goes here. So don't call it pinion and gear anymore. Only the notations will be synonymous. So for worm, the worm you have as a pinion, and this is for the gear. Right? So you can start noting the steps which we use to design in case of worm gear. So this is all for the terminology part. Only main key dimensions I have covered. And what is to note is for this lead, you need the number of starts. Right? It's a number of starts which is either 1, 2, or 3. How much linear uh, movement we can expect out of this arrangement. That's one thing to note. So coming to steps. So step one, as usual, there are a few extra steps in case of one gear, but I'll try to tone it down. This is easy. This is also easy, very easy. When you come to the first step, you can see that you don't need to do anything practically here. So we already know there is only one gear to design. Okay, worm. The dimensions of worm depends on the module. So you can get the module for screw, right? So instead of that, or we have only one gear, so we have to design only that gear. Okay, that we assume that as a weaker member and design based on that. Okay, worm you cannot design. There is no module. It's like just like a synonymous to a threaded screw. So therefore, the worm cannot be taken for any consideration. We take directly the worm wheel. So worm wheel is a weaker member, and we design it based on the worm wheel itself. So worm wheel synonymous to again the spur or a helical gear. So step two, similar to the all the previous gears, is the tangential tooth load. We are taking only tangential load into account. Okay, taking only the tangential load, the generalized formula which we used in all the previous sections, and service factor also same table 12.8 on where it is used and how much you are applying, and this is the Lewis equation for worm wheel. So worm wheel uses this equation. You can see it's simpler compared to both bevel and helical gears. So it's simple compared to both previous gears here, and velocity factors. So all these are given just below the equation. That is 12.53, and this is for the form factor y. So here you can see the value of capital Y here. The value of capital Y here is dependent on number of factors here. So either it is pi times y, so which we take it from table 12.5 to 12.6. So this is 12.5 to 12.6. Now, depending on number of teeth on the worm wheel, we take that particular value of y. If we know the number of teeth, or we can use this formula here. Okay, which is depending on the angle alpha here. Right. So what is angle alpha? It is the form, either 14.5 or 20 degree that we have already seen in the previous cases. The worm wheel is synonymous to spur, therefore you'll have a 14.5 degree or 20 degree angle. Okay, so that's step 2. And CV, the velocity factor, also given just below the main formula here, 12.53 for worm gear. So everything is one below the other. You can sequentially do. Only the thing is B is not given. So B will take same as all the previous gears. That is, we'll take it as 10 times a module. Right. And step 3 is the proportions of worm gear. It's step 3, proportions of worm gear. So this is dimensions depending on variety of factors, mostly on the module. So it depends mostly on the module here, but you can note here that there is no D2. So all things which are numbered 2, they are corresponding to the gear, that is a worm gear. So therefore, we need to design the worm gear diameter first. So that means once we know the module, we need to establish the number of teeth and find D2. So you need to have 2 dimensions in order to find the parameters here. That is D2 and M. So whatever dimensions you need, the key dimensions here, so we need two dimensions. That is D2, which is the pitch diameter of worm wheel, and M, which is the module. So we need 2 dimensions to determine any key dimensions here. So these are proportions for worm gears, and you have this is proportions for the worm itself. So again, for the worm, we only need the module. So once we have the module, we can find the key dimensions. Yeah, right. So module is all the thing we need to design some key dimensions. So as usual, this step 3 is the easiest step in the whole design process. You just have to find module and find the other proportions. Now going to step 4, so we design here the wear load. The wear load formula also you can see is very simplified. Just depending on the worm gear diameter, B would have already been found, and K you find using this table here, the 12.53, 12.30D. So depending on what your worm material is, and worm and gear material, combination of worm and gear material is, and depending on what is the uh, helical uh, angle of your worm, where it falls, either in this region. You just need to take that particular value. So the ones in the brackets are their second preference. So the outside ones, we take the value of K. So thereby we find what is the wear load acting on that particular arrangement. Okay, step 5 is the efficiency of worm gear. So here's where it's different than the previous ones. So this is step 4 till here. I think it's almost common for all the previous gears. But step 5 onward, you can see that it's different. You need to find efficiency here. So how efficient is your gear? Because heat generation and dissipation, as I said, is an important factor. So before we go to the next step, so we need to establish this efficiency first. So efficiency, you need mostly 2 parameters, which is mu, that is coefficient of friction, and you need gamma. Gamma is helical angle of the worm, and to find mu, there is another follow formula uh, just in the very next page, which is depending on the velocity. So if velocity of worm, whichever is applicable, we need to use that particular formula, and VR, where VR is the rubbing velocity. Rubbing velocity again dependent on the diameters and RPM of the worm, diameter and RPM of worm, then the angle, helical angle. Okay, so all parameters would be almost known. Just substitute this and find out what is the efficiency. Right, this is about step 5, and the next and the last step. So this is the last step when we start off with the numerical at the heat dissipation. The heat dissipation, so we have 2 formulae here. So first formula will find what is the value of Q. So we know mu Fn, this equation we use to find Fn. Okay, Fn is the tangential driving force. So you can see Fn here. Ft you would have already found. So we'll just use this part of the equation to get Fn here. So once Fn is found, we'll go on finding the value of Q, that is the amount of heat generated, which is in joule per second, and use these two formulae to find T2. So T1 will take some room temperature, and if here T2 is temperature which is generated after during the operation of the gear. So if this temperature T2 is greater than T1, okay, that means some amount of cooling is required. So that's how we utilize. We utilize all these three equations later on and find out whether cooling is required or not. Right. So that's it for the design procedure. You can start off with the numerical. Okay, you can note down the first numerical on worm gear. We'll start off with the first numerical. We'll know what to design. Okay, so design a worm gear that is directly given. This worm gear can be given as non-parallel, non-intersecting shaft with more keywords like very high reduction ratio, speed reduction ratio, so this kind of stuff. So it can be given like that. That's one option for instead of worm gear, or we may mention some application like a supercharger or even a crane or a valve, valve which operates water, or a mechanical elevator kind of a mechanism. So all these things are directly relate to worm gear, right? That's why I told you the application in the beginning. Then this is to drive to transmit 18 kilowatts from a worm rotating at 1400 RPM. See, always a worm means you note down for dimensions of 1. Okay, that is for pinion. So D1, N1 all goes for worm, and to worm wheel rotating at 40 RPM. So worm wheel, you can see the reduction. So see the drastic reduction in the speed all the way from 1440 to 40. That's a very high reduction ratio. Check for heating capacity. So this is what you will be asked primarily in case of worm gear problems. Okay, you can identify even using this thing. Whenever heating or heat dissipation related questions, so you can directly relate to that to a worm gear. So check for heating capacity and determine whether the design is safe or not. The design is safe or not means you just have to recommend design and then recommend the amount of cooling required. That's it. Worm is made of hardened steel and gear is made of phosphorus bonds. So gears, worm is made of hardened steel and the gear is made of phosphorus bonds. Right. So two different materials given for gear and worm. See, yes. A gear is made of bronze usually, not the worm. Right. So assume number of starts as 1. So number of starts usually given. Otherwise, you can assume the number as 1. So this just means that it moves 1 pitch per revolution of the worm. So that's what the number of starts mean. Okay, I hope it's taken care of. We'll start off with the numerical. Okay, so this is the first problem on worm gear. Let's see what is given. The data is power is given, which is 18 kilowatt. Then RPM N1 is given. So N1 is 1440 RPM. So I told you before, worm is 1. Designate worm as 1, and N2, which is the worm wheel or the gear, is 40 RPM. This is 40 RPM. And material. So material wise, worm is made of hardened steel. Hardened steel. Then worm wheel is phosphor. Right. And number of starts is 1. So number of starts is 1. Next, so we need to design the gear overall. That's the objective. Let's start off with step 1. The solution. Step 1 is the weaker member, right? To find the weaker member. So in case of worm and worm wheel arrangement, there is only one gear to design, as I told you. In the design of worm gear drive, worm gear drive, a worm gear is always weaker. Okay. So worm gear is always weaker, and we can say hence design is based on worm gear. Over here, in case design is always based on worm gear, so this step is mostly redundant. So just to make it synonymous to all the previous problems, no, so that's why we kept an additional step, step 1. The next is tangential tooth load. So this is to find, let's say, to find module M, and this is tangential tooth load. So again, as similar to the previous two, uh, 3 gears, tangential tooth load is also generalized formula once, and using the specified formula for the others. We just copy from previous one here. Just copy this formula here. This is generalized formula for tangential tooth load. Just taking that. Okay, this is first part. the tangential tooth load. So here we know power P is 18 kilowatts. Then service factor. Service factor depending on number of hours of use. So here, since it is not specified, I'm just taking 1.8. Okay, this is from table 12.8, as we have solved with all the previous numericals. Assuming 8 to 10 hours um, heavy shocks. This is assuming heavy shocks. You can refer to this in the table. So the service factor, which we have already done multiple times, and the velocity v. Let's copy this. Okay, so velocity here it is 2. The gear is designated 2, so therefore we'll put it as 2 itself. So N1 and T1. So in here we are not aware of the number of, that is the diameter. So we'll change this diameter to Z2 and M. Z2 and M instead of the diameter D, since we don't know either of them. So now we need to find Z1 and Z2. Z2 is not known to us yet. Also, we know that I, which is the velocity ratio, so we know that is N1 over N2. So N1 over N2 is equal to, let's copy this, is also you can say is Z2. So this here is Z2 over Z1, which is the number of teeth between the worm and the worm wheel. You can see in this question what it is number of teeth. The worm is made up of 1400 rpm. Worm is rotating at this rpm, and the worm wheel is rotating at this 40 rpm. So these two revolutions you need to make a note. Okay, so this equals to, so we have the worm rotating at 40 rpm, and sorry, this is 1400. So this is corresponding to the worm wheel, and this is for the worm. So 1400 over 40, going to calculate, and so what you get here is 36, right? So with this we can find what is the number of t, that is Z2 over Z1. Okay, so in case of worm, no, so what happens is, depending on the number of starts, we can assume this value here, that is Z2 over Z1, as Z1 as 1 itself. Okay, so this we can write directly as Z1 as 1, because the number of starts here given in the question, you can see here, is 1. So therefore you can assume this number 1, whatever the number of starts are, because lead is equal to 1 times the pitch when it comes to the movement. So this is equal to 36. So therefore, in this case, Z2 we can equate as 36 itself. Okay, the number of teeth on the gear will be 36. So once we find the number of teeth on gear, so we can use it in the velocity and ultimately determine what is the tangential tooth load which is acting on that particular gear tooth, right? So we'll take this equation here. So let us solve for velocity now. So this equals pi times Z2. Now we know the value is 36 times module and N2. The RPM given the data. N2 is 40, is rotating at RPM of 40. Right. Now we can calculate the velocity. Just calculate and let me know in the group chat what is the value. Now continuing, once you have found all of this, let's substitute in the tangential tooth load equation here and find out what is the tangential tooth load. That is part 1 of this step 2. Right? Okay, this is synonymous to the this numerical. Now you can take it as equal to this here. Okay, this gear. So this here is rotating at an RPM of 1440. This is the worm, which is designated as 1, and this is rotating at an RPM of just 40. So you can see how drastic the speed reduction is in case of worm and worm wheel, right? So very drastic speed reduction, and you have a very high heat generation here. So more the heat generation, more dissipation is required. As you can see, this crane or a hoist, you can say, is just left open to the atmosphere, so that there is heat dissipation happening, and the speed reduction ratio you see is almost 36, which was never seen before in all the previous cases of gas which we saw, right? So, and this is moving only, rotating only in an RPM of 40, and this is rotating at an RPM of 1440. So very drastic reduction in speed ratio. So let's go back to the problem. Okay, it's 5 times 36 times 40 over 60,000. It's giving me just 0.07754 times module. So this equals to, I can put a, I can copy the same thing here. Okay, this power P is 18 kilowatts into service factor 1.8 into 1.8, and velocity we have just found. Velocity for this gear is really low, 754 times module. Okay, so simplify this. Let me know in the group chat. Then second part of this step 2 here will be tangential tooth load. This is using Lewis equation. So we are using Lewis equation in the step 2, so as we have done for the previous numericals. So let's just go for step 1, step 2. Right. So this is the equation. is in the data handbook, we use 12.53, which is designated for worm gas. We'll note down the second part of this equation here. The Ft is sigma d, Cv, By, and m. So we'll type the same thing here. Ft, according to, that is the tangential tooth load, according to Lewis equation, is sigma d Cv By m. Cv B capital Y and M. So we'll just subscript this D here and subscript the velocity factor V. Right. So this is given in equation 12.53a. Right. So now one by one we'll determine the values here. So sigma D is, what was the material for sigma D? Again, we are calculating for 2. Make a note. We are calculating for the worm wheel. D2 is phosphor bronze. So we'll subscript that also. This D2, which is material for phosphor bronze. So for phosphor bronze, not put it here. Right, I think we can see in this table phosphor bronze gear. So phosphor bronze, the material, the value of the allowable stress is 82.4. So 82.4 is the allowable stress for a phosphor bronze material. So let's note down this value for the allowable stress, static stress. Again, this is from table 12.7, which we have been using since last 3 types of gears. This sigma D is 82.4. It's Newton per mm square. Right. So this is again from table 12.7. So that's where you take the material properties of all the materials. So sigma D we have found. Next, Cv, that is the velocity factor. So Cv, if you go back to the steps, right. So here you can see the velocity factor, number of teeth on worm gear plus this will usually exceed, but we don't have the form of teeth. We can also use here the velocity factor Cv, which takes into account also the dynamic load. So we can use the first value here. So why the Cv we'll use from this equation. So either of these two we can use, but is not mentioned whether to take into account dynamic load or not. So therefore we'll use this equation here. So Cv is 3.05 over 3.05 plus V. Small v. Velocity is known, therefore we can use 3.05 over 3.05 plus velocity v is this thing. So this we are getting in terms of module m. So CV, B will assume 10m, and capital Y is we'll take the usual pi times y, pi times small y. Then module as it is. Y value need to note down again from the table here. So Z2 I think is already found. So 36, right? So from table 12 point, there's another table, right? I think we'll stop at this point. We'll continue this the next class.